opening months of 1945, the frigid waters off the Japanese coast became the setting for a pivotal moment in aviation history, when an American F4U Corsair was forced to ditch following an engine malfunction. As the pilot ejected and the fighter settled into the Pacific, Japanese patrol vessels quickly converged on the site to retrieve the floating airframe. This recovery operation granted the enemy one of the most critical intelligence windfalls of the war's closing stages, placing a prize of immense value directly into their hands. For nearly 3 years, Imperial pilots had engaged this formidable machine in the skies above the Solomon Islands, Rabaul, the Philippines, and eventually the home islands themselves. Through bitter experience, they'd come to respect its blistering speed, overwhelming firepower, and a rugged construction that seemed impervious to damage. Yet, until this moment, they had never possessed a pristine specimen to analyze, measure, and flight test in order to comprehend the true extent of the technological gap that had widened between the two nations. The narrative of Japan's encounter with the F4U Corsair transcends the simple acquisition of an enemy asset. It marks the chronicle of a stark technological awakening. When aviation specialists finally confronted the sheer magnitude of American industrial and engineering supremacy, the experience was sobering. By dissecting this fighter, they unearthed undeniable truths regarding manufacturing precision, advanced material science, and design philosophies that completely dismantled their previous assumptions about their own industrial capabilities. The airframe recovered by the salvage crews stood as the apex of American fighter development, a design that had matured from a radical 1938 concept into one of the conflict's most dreaded combatants. Instantly identifiable by its inverted gull wings and the massive Pratt & Whitney R2800 double Wasp engine, the aircraft delivered revolutionary performance metrics. Crucially, it achieved a synthesis that Japanese engineering struggled to replicate: a perfect equilibrium between high velocity, heavy armament, extended operational range, and structural resilience. The Corsair's origins can be traced back to a request issued by the Navy's Bureau of Aeronautics in 1938, which called for a fighter capable of breaking the 400 miles per hour barrier in level flight. This requirement was nothing short of revolutionary for the era, considering that most contemporary aircraft struggled to reach even 350 miles per hour. Furthermore, the Navy demanded a comprehensive performance package that included a low stalling speed for carrier landings, a range of 1,000 miles, heavy weaponry, and the capacity to deploy bombs. The response from Chance Vaught was remarkably audacious, as chief designer Rex Beisel and his team chose to construct their machine around the most powerful propulsion system available, the Pratt & Whitney R2800 double Wasp. This 18-cylinder, two-row radial engine generated 2,000 horsepower, an output nearly double that of most rival fighters of the time. To effectively harness this raw energy, the engineers utilized a colossal propeller measuring 13 feet and 4 inches in diameter, the largest ever integrated into a fighter aircraft. Fitting such a massive propeller presented an immediate engineering dilemma: how to ensure sufficient ground clearance without compromising the structural efficiency required for carrier operations. Beisel's team devised a brilliant solution that became the aircraft's signature feature: the inverted gull wing, which angled sharply downward from the fuselage before leveling out to form a distinctive M profile. This configuration facilitated the use of shorter, sturdier landing gear while accommodating the propeller, and the angle at the wing root created optimal aerodynamic conditions that significantly minimized drag. The prototype, designated XF4U1, took to the skies on May 29, 1940, under the control of Lyman A. Bullard, Jr., the chief test pilot at the factory airfield in Stratford, Connecticut. During a subsequent test flight between Stratford and Hartford on October 1st, the aircraft utilized a tailwind to achieve a ground speed of 405 miles per hour, making headlines as the first single-engine American fighter to surpass this milestone. Although the actual maximum level flight speed was 378 miles per hour at 23,500 feet, the performance remained exceptional for 1940. Production models began reaching operational units in late 1942, with Marine Fighter Squadron 5 MF-124 deploying the first combat-ready aircraft to Henderson Field on Guadalcanal by February 12, 1943. However, the Corsair's introduction to combat was disastrous. During the engagement on February 14th, known as the St. Valentine's Day Massacre, American forces suffered a 9-to-1 loss ratio. 2 Corsairs, along with multiple P-38 Lightnings and P-40 Warhawks, were downed, while the Japanese lost only a single 0, a defeat so severe that daylight bombing missions to Bougainville were suspended, pending a tactical review. This early failure demonstrated that superior technology provides no guarantee of victory without the requisite tactics and pilot experience. American aviators quickly adapted, realizing that the Corsair was not designed for low-speed dogfighting, but rather for boom and zoom maneuvers, where it could exploit its ability to outdive, outclimb, and outrun any Japanese opponent. The new doctrine emphasized maintaining a speed and altitude advantage to dive on the enemy and deliver a lethal blow, then using superior momentum to disengage before a counterattack could be mounted. Second Lieutenant Kenneth A. Walsh of VMF-124 validated these methods, becoming the first Corsair ace on May 13, 1943, and eventually tallying 21 victories. As the war ground on through 1943 and 1944, the aircraft's reputation soared, particularly among Marine squadrons operating from hastily constructed coral airstrips in the Solomons. The Corsair proved exceptionally rugged, absorbing battle damage that would have obliterated lighter Japanese airframes, while continuing to fight effectively. To deliver its overwhelming offensive punch, the standard variant relied on 6 50-caliber Browning machine guns, with the 4 inboard weapons carrying 400 rounds each, and the 2 outboard guns holding 375, totaling 2,350 rounds of ammunition. Later iterations, such as the F4U further escalated this firepower by replacing the machine guns with a battery of 4 20mm cannons. While many pilots favored the reliability and ammunition capacity of the 50-caliber weapons, the Corsair's versatility extended far beyond simple air combat. By the middle of 1944, these aircraft were regularly outfitted with heavy external ordnance, carrying 1,000-pound bombs on centerline and wing racks, alongside 8 5-inch high-velocity aircraft rockets, or napalm canisters. This evolution into a fighter bomber made the Corsair an indispensable asset for close air support during complex amphibious operations. Throughout the Okinawa campaign in 1945, these machines executed thousands of ground attack sorties, a relentless effort that earned them the affectionate nickname Angels of Okinawa from the grateful infantrymen they protected. However, the terrifying reality faced by Japanese pilots in the skies revealed only a fraction of the Corsair's true story. From the cockpit of a Zero or other fighter, an adversary might perceive an opponent that was faster, stronger, and more resilient. But fully grasping the engineering prowess behind these advantages required a physical examination of the aircraft itself. Japan's capacity for such detailed technical analysis was concentrated within 2 primary institutions, the Yokosuka Naval Air Technical Arsenal south of Tokyo and the Army Aviation Technical Research Institute at Tachikawa. Throughout the conflict, these organizations had been meticulously studying captured Allied hardware, recovering whatever examples could be salvaged from battlefields across the Pacific. Although their work had yielded significant intelligence regarding American capabilities, the majority of their subjects were damaged fragments or incomplete wrecks salvaged from crash sites. Consequently, securing an intact, operational example of a frontline American fighter, represented an extraordinary and rare opportunity for their investigators. The Japanese Navy's facility at Yokosuka had been at the forefront of technical research since its reorganization as the Kaigun Kokusho Naval Air Arsenal on April 1, 1932. By the height of World War II, this massive complex employed thousands of skilled engineers, designers, and technicians dedicated to advancing naval aviation. Although actual mass production was typically contracted to major industrial firms like Aichi, Nakajima, and Mitsubishi, the arsenal itself designed numerous Japanese naval aircraft. The engineers at Yokosuka were seasoned professionals who possessed a mastery of aircraft design at the absolute highest level. When a salvaged Corsair finally arrived at Yokosuka in early 1945, it stood as one of the most modern American fighters yet recovered in relatively intact condition. Although the airframe had sustained some water damage during a forced landing, the fundamental structure remained remarkably sound and ready for analysis. Recovery teams had acted quickly to prevent the aircraft from sinking completely, allowing the fighter to be transported to Yokosuka's secure technical zone for inspection. The initial assessment focused on its general state, confirming that despite the immersion in salt water, the vast majority of the Corsair was intact. While the massive Pratt & Whitney engine would necessitate a complete disassembly and cleaning, the airframe itself showed no signs of combat trauma, which was a crucial distinction. Previous examinations of Allied captures had often been complicated by heavy damage, making it nearly impossible to differentiate between intentional design features and the chaotic results of battle. Japanese specialists commenced their work with systematic photography and precise measurements, recording every dimension down to the last fraction. They noted a wingspan of 40 feet 11.7 inches, a length of 33 feet 4 inches, and a height of 15 feet with wings extended, or 16 feet 2.3 inches when folded for carrier storage. The distinctive inverted gull wing configuration immediately captivated the attention of the technical team. While the Japanese designers fully grasped the aerodynamic and structural benefits of this layout, they also recognized the immense difficulty involved in its manufacture. Creating such compound curves and precise angles required sophisticated tooling and quality control that most Japanese factories could not reliably achieve at that stage of the war. The examination uncovered a detail that particularly surprised the technical team. Despite the advanced nature of the Corsair, specific sections of its outer wing surfaces were covered in fabric rather than metal. This fabric covering was found aft of the main wing spar and armament bays on both upper and lower surfaces, as well as on the control surfaces, including the ailerons, elevators, and rudder. Japanese aviation specialists initially found this puzzling, given that by 1944 and 45, nearly all modern fighters utilized all-metal construction. However, further analysis revealed a sophisticated reality. The fabric covering was a deliberate design choice, stemming from the aircraft's development period between 1938 and 1940. This approach reduced weight in areas where structural loads were minimal, thereby conserving aluminum for critical load-bearing components. The fabric was a specially treated material that, when properly applied, offered adequate strength and weatherproofing while weighing significantly less than metal skinning, representing a mature understanding of resource allocation for optimal performance. Disassembly of the wing structure exposed construction methods that the technical personnel found to be both impressive and deeply troubling. The main wing spar, the critical element responsible for carrying flight loads, was a massive forging of exceptional quality, proving that American metallurgy could produce aluminum alloy forgings with strength characteristics the Japanese facilities struggled to match. The dimensions and load-bearing capacity of the spar exceeded anything found in comparable Japanese fighters, illustrating a fundamental industrial difference. While Japanese manufacturers were increasingly forced to rely on built-up structures assembled from smaller parts, American industry demonstrated the capacity to produce large, complex forgings with unwavering quality. The internal structure of the wing demonstrated a similar level of sophistication, with ribs stamped from aluminium sheet showing remarkable precision and consistency. Each rib was virtually identical to the next, a testament to manufacturing processes governed by tight quality control, an area where Japanese production increasingly struggled as the war progressed. Attention then turned to the Corsair's armament. 6 Browning A&M 250 caliber machine guns mounted in the wings, representing a formidable array of firepower. The installation was compact, reliable, and designed for ease of maintenance. But what truly struck the Japanese examiners was not merely the destructive potential, but the sheer completeness of the system. The aircraft's armament mechanisms, ranging from ammunition boxes and feed systems to the ejection of spent cartridges, were engineered to function with seamless integration. The guns themselves stood as exemplars of precision manufacturing, showcasing a level of reliability in American ordnance production the Japanese industry could only envy. The Browning M2 machine gun, a mature design refined over decades of development, was produced by the millions with extraordinary consistency. Technicians examining these weapons recognized manufacturing techniques and quality control standards that their own factories struggled to replicate on a consistent basis. When inspectors discovered a 150-pound armor plate protecting the cockpit and a 1.5-inch thick pane of bullet-resistant glass behind the windscreen, it reinforced their impression of a distinct American design philosophy. Japanese fighters had largely sacrificed heavy armor in favor of lighter weight and superior maneuverability, a strategy that the early success of the Zero seemed to validate. However, as American fighters evolved to become more powerful and heavily armed, this lack of protection proved fatal. The Corsair demonstrated that with proper engineering, substantial defensive armor could be incorporated without sacrificing performance, a feat made possible by the massive output of its power plant. That power plant, the Pratt and Whitney R2800 double Wasp, dominated the technical examination and represented the absolute peak of American aero engine development. With 18 cylinders arranged in 2 rows of 9, displacing 2,800 cubic inches and generating over 2,000 horsepower, this engine was a masterpiece of mechanical engineering. Although Japanese engineers had encountered this model in captured wreckage before, they had never possessed an example in good enough condition to allow for such a thorough and revealing analysis. The construction of the engine unveiled manufacturing capabilities that seemed almost incomprehensible to the observers. Cylinders were machined with precision tolerances measured in thousandths of an inch, while components such as pistons, connecting rods, and crankshafts displayed surface finishes and dimensional accuracy the Japanese manufacturers found difficult to achieve. The 2-stage supercharger system, designed to maintain power at high altitudes, featured complex internal passages and precisely fitted rotating components, technology that Japanese attempts had largely failed to master due to industrial limitations. Perhaps the most impressive aspect was the engine's sheer reliability and consistent power output. American radial engines routinely delivered their rated horsepower for hundreds of hours between overhauls, whereas Japanese counterparts, even when new, often failed to meet theoretical ratings and required frequent maintenance. The consistent performance of the R2800 was the result of superior metallurgy, advanced lubricants, precise manufacturing, and sophisticated quality control protocols. The propeller system proved equally illuminating. The 13-foot 4-inch Hamilton Standard hydromatic propeller, with its variable pitch capability, represented a leap in aerodynamic design and hydraulic control. While Japanese engineers understood the theoretical principles behind such a device, they lacked the facilities capable of manufacturing large propellers with the necessary precision. This pattern of excellence extended to the complex landing gear mechanism and the cockpit, which presented an array of instruments and controls far exceeding the comprehensive standards of Japanese fighters. The fuel system was notably advanced, incorporating self-sealing tanks constructed from multiple layers of rubber compounds that swelled upon puncture to prevent catastrophic fuel loss, a technology largely absent from Japanese aircraft. Similarly, the electrical system was robust, powering extensive onboard equipment through high-quality wiring that was properly insulated and meticulously organized. Above all, the examination revealed a pervasive quality in materials and manufacturing. From major structural elements to the smallest fasteners, every component exhibited uniform aluminum alloy properties, properly heat-treated steels, and professional surface finishes. The aircraft felt substantial and built to last, standing in sharp contrast to the reality of Japanese aircraft production in 1945. Wartime shortages had forced the increasing use of substitute materials, while aluminum quality had deteriorated and skilled workers had been conscripted into service. Factories operated under the constant threat of American air raids, causing quality control to suffer as production schedules prioritized quantity over precision. This technical evaluation of the captured Corsair occurred against the backdrop of Japan's imminent defeat, with American B-29 bombers systematically destroying cities and the Imperial Navy shattered at Leyte Gulf. With the Philippines liberated, Iwo Jima fallen, and Okinawa under assault, the examination took on a somber significance. It was not a mission of intelligence gathering for future victories, but a final reckoning with technological reality. Japanese engineers at Yokosuka and Tachikawa compiled technical reports detailing measurements and manufacturing techniques, offering assessments that, while professional in tone, could not hide the grim implications. In nearly every category, American technology exceeded Japanese capabilities, revealing a gap created by years of industrial development, massive investment, and resources that Japan simply did not possess. By the end of the war, in August 1945, at least 2 Corsairs had been captured by Japanese forces. Photographic evidence showing captured aircraft with patched wings and fuselages suggests that technical personnel managed to repair at least one airframe to a flying condition. While it remains uncertain whether actual flight testing took place, these repair attempts indicate a serious and determined effort to render the aircraft operational for a final, comprehensive evaluation. When American occupation troops entered the Yokosuka Naval Air Technical Arsenal in September 1945, they uncovered a sprawling cache of evidence detailing Japan's technical intelligence operations. The facility was littered with captured Allied aircraft, while a trove of reports, schematics, and photographs revealed intense efforts to reverse engineer foreign technology. Intelligence officers immediately seized these materials, recognizing them as a vital key to understanding exactly how much scientific insight their former adversaries had managed to glean from the captured machines. The analysis of the F4U Corsair by Japanese engineers represents far more than simple military espionage. It epitomizes the immense technological chasm that had widened between the two nations by the war's conclusion. When the Corsair first debuted in combat in early 1943, skilled Zero pilots could still hold their own through superior maneuvering and tactical brilliance. However, by 1945, the scales had tipped so drastically that even veteran Japanese aviators flying updated machinery found themselves hopelessly outmatched against competent Corsair crews. This disparity was driven by a combination of the Corsair's engineering dominance, vastly better pilot training, and the sheer numerical weight of the American forces, creating a scenario where victory was statistically impossible for the defense. The results were staggering, with the Corsair boasting an official kill ratio of 11-1 against Japanese fighters. In total, U.S. pilots claimed 2,140 enemy aircraft, while suffering only 189 combat losses of their own throughout the Second World War. Such lopsided figures reflected the dominance of the entire American war machine, from superior logistics and production capacity to advanced technology at every operational tier. As Japanese engineers dissected captured Corsairs, they acutely understood these realities, measuring the performance gap and analyzing the stark differences in manufacturing quality. Their technical assessments essentially became admissions of defeat, documenting the impossibility of competing with the industrial juggernaut they had challenged. The Corsair's operational life extended well beyond the surrender of Japan, seeing extensive action during the Korean War from 1950 to 1953. Even as the jet age began to dominate air superiority missions, this piston-engine veteran proved exceptionally capable in ground attack and close air support roles. Its utility persisted globally, with foreign air arms like the French Navy deploying the type in various colonial conflicts throughout the 1960s. In a final historical twist, the Corsair saw its last combat during the brief Soccer War between Honduras and El Salvador in July 1969. On July 17th of that year, Honduran Captain Fernando Soto, piloting an F4U downed 3 Salvadoran planes, 2 of which were, ironically, FG-1D Corsairs. From its maiden flight in 1940 to these final engagements nearly 3 decades later, the airframe cemented its legacy as one of aviation's most enduring and successful designs. For the Japanese, studying this aircraft was a crucial component of their reckoning with technological reality under the American occupation. Engineers and scientists, who had previously battled severe material shortages, began collaborating with occupation authorities to reconstruct their nation's industrial base. The insights gained from analyzing American hardware like the Corsair profoundly influenced their post-war manufacturing philosophy, shifting their focus toward new standards of production. The obsession with precision, quality control, and continuous improvement that defines modern Japanese industry can be traced back to these moments of analyzing American output. The Corsair recovered in early 1945 was not merely a downed enemy fighter. It was tangible proof of the engineering sophistication and manufacturing excellence that Japan had desperately strived for, but failed to achieve during the conflict. While these realizations came too late to alter the war's trajectory, they were instrumental in shaping the peace that followed. By dissecting this American machine, Japanese engineers were forced to confront the sheer magnitude of the challenge they had faced. They realized that no amount of courage or skill could surmount such massive industrial and technological disparities. Ultimately, this narrative concludes not with a military triumph, but with a somber, professional acknowledgement of superior capability. The technical reports unearthed by occupation forces now rest in archives as silent witnesses to that pivotal moment when one nation's experts came face to face with another's true potential. Although the specific Corsair they examined was likely scrapped during the chaotic post-war years, its legacy endures in the lessons it imparted regarding the power of well-resourced, sophisticated manufacturing. While Japanese aviation would eventually rise again, the engineers of that era vowed never to underestimate what American counterparts could achieve when backed by sufficient industrial capacity and scientific knowledge. The 1945 examination of the F4U Corsair stands as a watershed moment where the establishment finally grasped the technological chasm that had opened during the war. It was a lesson written not in propaganda, but in the undeniable reality of aluminum alloys and precision forgings that spoke louder than words about the true nature of American industrial power.